Okay, so I think we've gone live here. Just waiting to see if everything's up there. Just do a hello over there. And this is a Python programming video, but actually I'm not sure how much Python we're going to be doing at this point, but we're going to be looking at neural networks, which is this section here, and I'm going to revamp a earlier chapter because this is chapter 2, but that's what we're going to look at to start at least. And let me just close this down because I've got some background noise which I don't want to have. So if I just close that down, there we go. Work related stuff. We're going to look at this back propagation and how the algorithm works. I'm going to read through some of this documentation here, but basically what we're going to be looking at is this piece here, which is the cost function with respect to omega, which are the weightings basically. So, and like, what does that all mean? And I've got this on the side here, which is it's actually my math notation thing, but I'm going to make a little new chapter here, and I'm going to call it back propagation. I spell it as 2 words, but we see here sometimes it's referred to as one whole continuous word, back propagation. So, and that will actually be a title here, so let's just titleize it. So that's our little back propagation section, and the reason I'm doing it like this is because I can, well, I might even start like using some copies and pastes and things, but I can sort of like copy and paste these functions. So in fact I might start that over here, as in what we're actually talking about over here, which is, and we are going to get to the nitty gritty of it, but it's kind of like, at least I saw the crux of this down here, which is this component, which is the notation, and that's kind of like the key to it, and how that notation links in. So this W, L, J, K, this whole complex looking thing, what that actually means relative to this picture over here, in terms of that the omegas are the weightings, but it's the weighting for the kth neuron, so the kth neuron in the layer of L minus 1. So if this is layer L, this is L minus 1, that's the L minus 1th layer. And maybe I'll separate those with, like, so our layers are here, layer 1, layer 2, layer 3. So that's kind of like what this person's describing here, and so that's our kth neuron and how it's related to the jth neuron. So, you know, the JIs basically. So this is KI. So like you've got K1, K2, K3, so you'd have J1, J2, and so forth, J2 and J3, etc., all the way up to the nth neuron. So J of n will be like your last neuron, your nth neuron there. I've got to be careful not to use any other letters twice, but that's Jn. And likewise for all of the Ks. It's kind of like this relationship between this neuron, if I use maybe yellow here, hopefully, like, so like this relationship to the next layer. So it goes out there and it goes out there, and which other neurons it's linked to, so, you know, in this case all of them and so forth. So that's the K1th neuron over here, and you know how it connects to all of these, and this is the K, well, I'm going to call it even K0th neuron, because depending on if we're talking coding or mathematics, but the next one here will be the next one up. So like, for example, if that was K1, this is going to be K2, and so like again how that links in. And if I use a different color, so like we can see already here, you know, it links into the first J neuron, and then the second one, and then the third one, and these are all in this level over here, and the kth ones are in the earlier level, L minus 1, and finally over here. So that's basically what we're sort of like looking at. Very complicated, sort of like drawing wise. Let me hit an undo on that if I've got an undo. Very complicated drawing wise, but once you get to grips with the notation, and that's kind of like what I'm going to try to attempt to do, at least in this particular video, hopefully it'll become a little bit easier. So, and like, you know, I've just seen this for the first time. I've not read anything. Like, those people that do follow will know that everything that I do, or a lot of the stuff that I do, this is completely live, and I haven't pre-practiced it, so I'm going through this as somebody who's reading this for the first time, as an interest to see what happens. So anyway, let's do delete of all of those bits, and then delete of that, and let's go to, oops, that's my actual studio, so I can open it on the side actually, that's a live stream. Quite nice to have the live stream there. Okay, I've got a new live stream. And yeah, that's pretty much it. So I'm going to start going through that. If anyone's got any comments and so forth, feel free to make your word, say your piece. So I'll post that out to Twitter as well. There we go. If it does, no, it doesn't. Okay, I'll hit cancel there, because I'm just going to try and log into it. Well, maybe I will. I'm going to try and attempt to post this straight out to Twitter. So let's try and do it. It's going to try and sign me in, basically. You'll see part of the signing in process there. It's opened up a nice big thing there. Sign in as the left goes. So just sign in. And then sign in again. Presumably it's launching. And I guess accept. I did try to share it to Twitter. No, it's going to keep on doing that. Okay, so that's not happening. It's not happening in that way. But I can post to Twitter, which is now x.com at some point, and I'll post a live feed there. So the stream is live now, and paste that in there and hit post. There we go. So that's all posted out, and people might join, people may join, may not join, but feel free to jump in with comments. So let's. I'll try not to jump around too much, but there will be a bit of jumping around. I'm going to get this notation in here. So I copied this, but it's literally just so that I'd have the formulas here. So let's just actually, we'll define a W over there, and where is our formula there? Menus. I don't know if I've got the formulas over there. I wonder if the formula bar will pop up when I click on one of these. No. So let's try and get our formulas working. Insert or view equation toolbar. There we go. Okay, the equation toolbar is the way to do it, not insert. So what I was trying to copy. So basically, the first thing is to get that notation in. Once it's in, once you've gone through the pain of it the first time, it's fine afterwards. But basically, we're going to need some notation that looks like this, which has got superscripts and subscripts, and the superscripts. I'm going to try and maybe I'll copy the notation. If I can get there. Okay. You know what I'm going to do? I might have to delete the whole lot of that and do this bit over there, which is W, and then A, comma B. I'm going to just do A, comma B to start with, and then C over there. That's kind of, that gets us in. And that's kind of like our basis function. So this is, and in fact, I'll give it a name here. So let's begin with the notation. First, the weights in a neural network in an unambiguous way. Okay, the weights in neural. Okay. Right. Okay. There we go. maybe I can copy all of this because this is all here. Because hopefully if this does paste in, it will save us a lot. Paste without formatting. Okay, which is not bad actually. Okay. We can just say let. We can actually do this. We can define, and then we'll define, copy that out here. Oops, Control Z. I just want to take that whole formula actually, X, and paste it over here. But we're going to define this formula here, or we're going to define this notation as follows, right, which is this, where, and then W, where this W denotes the wait for the connection of the case neuron. So I'll make that, I guess I'll make that bold, but where W denotes the wait for the case neuron 4, right. Okay. From, okay, let's get it like this. I'm going to insert some bullet points here. The case neuron, okay, and then in the I-1th layer, so let's get the layer into the line, to the jth neuron in the L-1th layer. And I need to get all of these notations correct as well, so let's just go across. L is at the top and J and K are the two indexing things, so we are indexing here. That's a J and that's a K, and over here is going to be an L like that. Now I'm using a lowercase L. I just want to just check. Well, yeah, the lowercase L is being used there, so fine, that's cool. You just got to be careful here because that is an L, not a number 1. A number 1 looks like this, which is kind of like similar. Like I'm sort of like biased sometimes to use the L like that, but I'm going to do that. But we will superscript this so that it is a bit clearer. And I think, I don't know if I can do that. Format options, no, I can't do it like that. But I can do format, text, and superscript. So that's the ELF thing there. I think it's controlling something. I can't remember what it was. Not that one. Oh, it will actually be on there. It's control and dots gets you superscript, and control and comma gets you subscript. So control dot. Oops, let's go back into the document there. Control dot. No, it didn't do it. Format text. Control plus dot should get you a superscript, but it's not doing that. So we did that and got the subscript, but the superscript isn't coming about. So annoying. This is control plus dot. Maybe it's, I wonder if it is. Okay, it's not the keyboard dot, but it's the mousepad dots. That's interesting. The keyboard dot doesn't do it, but the mousepad dot does. Okay, but anyway, so we're beginning to have our notation here, and this is the case neuron. And it's on the L-1th layer. We were talking about the layers before, so I can sort of like start to draw it out, I guess. Maybe in fact even, I mean, I could nick that picture and annotate the picture, or I could redraw the whole picture. If I was to nick this picture, would I get, I mean, I get a similar type of thing here, but let's just draw it out then in that case, which is insert a drawing So just basically a new drawing over here. And what we're going to have is a bunch of neurons. So there we go. The advantage of this is if I've done it properly, let's just control page back there. There's 3 neurons. There's 3 neurons here and there's 4 neurons here, because there's nothing to say that you have to have more or less, or like the number of neurons that are available. So we can have as many as we like here. So I'll go here and I'll start with, well, I have 4 and I'll have like 10 over here, for example. So let's just copy this and paste it over there. And in our next layer, we will have, I wonder if I can make them smaller even. There we go. I'm trying to make sure that they're circles and filling them up with slightly different colours, just for the sake of showing that they're different, and copy paste to, there we go. Okay, we don't need to have a 1-to-2 relationship, but that's just, I've just drawn something there, and this is just for the, like, this is for our picture really, but it just helps us define things. So we can see as this is being built now, if I do text here, this is the layers. So this is the L-1 layer. Layer L-1. And then if I copy that across to here, this is going to be layer L. And if we were to have, because we can have more layers, but we're literally going to be talking about the relationships. This is layer L, but we could have, copy this, paste this here, which is, we could have another layer if we wanted to over here, which is layer L+1. So we can sort of like get the idea of what the layers are doing, because the layers are kind of sequentially going across like this, from there and to there and so forth. So that's kind of like how the layering actually looks. And just if I go back there, well, there is actually a 3rd layer. Good. So yeah, we can keep doing that. So I'm going to go through on this just to complete this. Again, I will select nick those 2 and paste it and move it over there. And somehow this next layer, which is the L+1 layer, and again I'll colour them in a different sort of like colour just to show that they're slightly different. So that's our final layer over there, and that's pretty much it. So let's just now, I don't know if I can, I don't think I can actually get a formula in there, but our weight for any one of these is going to be, so what I can do quite nicely here on the actual chat is I can sort of like show the connection. So here's the connection of the first layer, of the first neuron, and this is the kth neuron. So this is a K. I don't know if I can get capitals in there either. Control dot. Oh, it does let me do it. Fantastic. So that's the kth neuron. Instead of putting kth, actually, I'll actually control comma, I'll turn it into a subscript, and we'll sort of like put K1 here, because that's K1. Well, we'll be this is the first neuron here, so let's just call this K1. We've got to be careful about these, but hopefully we'll get the notation right. Copy this, paste this down. You can sort of like see, and it's after the hard labour of getting everything sort of like set up initially. This is K2. We can see that this becomes a little bit easier. Copy that and paste it, and I'll sort of like go down to the bottom, because we get the idea that but this one here is going to be like the nth neuron, however many neurons are in there. So that's our K neurons over here, and these ones, I can actually copy this as well, so copy paste. These are our, if I can go into there, J. So these are our, I'll keep a lowercase j for what that's worth. So that's our J1, and that's going to be J2. I've got a little bit more room, so I can have a J3 over here. And finally, we can have a JN down the bottom. So we sort of get the idea that these are our Jth neurons, and it goes all the way from like 1 to N. In coding, we need to remember that we start normally at index 0, so that would actually be 0. So I might come back and change that. We'll just see on that count. But these are our K neurons, and the K1 links to J1, to J2, to J3, and so forth. So we could actually build out, oops, didn't do that well, so hit delete on that. Oh, that's because that's in the way now. Fantastic. Let's get that there. Okay. How annoying. I have to shrink all of these to get them so that I can do the drawings correctly. Unfortunately, I couldn't get away with having this outside, so they're all shrunk now, so that's fine. It just gets in the way of the connectors here, so now I can connect nicely. Hopefully, there we go. Got to be careful because all of these as well, I'd have to shrink all of these if I want to be able to reconnect as well. So I'm going to shrink all of these over there. Didn't think about that in the beginning, but that's important. And this keeps on fanning out. That's the whole issue with this, or not the issue, but that's actually what happens. That's part of the neural network. So oops. Control Z there. Right. There we go, and so forth. So we get the idea that that keeps going out, and I'll do another fan just so we can see over here. But let's, if I can connect that over there, and that will connect over there. Good. Yeah, we can do that. We can sort of like see this one if we can. I have to do it like this. There we go. So that's this one over here. And what we're talking about in any one of these is this is the connection, or this is the RW. So I've got to be careful again on one thing, which is that this is just wide enough that we can actually fit it in. So there we go, it fits in. Now, this here will be, well, we can take any one of these lines, but it's going to be W over here. And then we're going to, I might make this a bit bigger afterwards, I'll see. But W, and then we're going to have a subscript here, and it's going to be, for example, W1 to, in our particular case, we've got 1, 2, 3, 4, 5. We'll call it, so W1 to W5 of layer, and I will struggle a tiny bit to do this, but I'm going to do it like this, which is Control and comma for a superscript of layer, and this is, I think it is 1 over there. So it's going to look something like this, and this relates to this particular line over here. So it's like, maybe I'll highlight that one in blue or bold or something. Wait, so I make this one a little bit thicker. and I will colour a different colour as well. It's kind of like blue, and this here now, if I wonder if I can make all of the text blue. Blue. There we go. So we've got a whole bunch of blue text there, and I wonder if I can increase the sizes as well. Yeah, we can to an extent. There we go. So a reasonable effort there, and I just want to check on one thing just to make sure I've done one thing correctly there, which is 3. It's referring to, so this particular line here is referring to the next layer on. So we need to, in order to be consistent here, we're going to refer to this as 2, because we're talking about layer 2. So we can actually give these layers numbers. So this could be 1, this can be 2, and this is going to be 3 in our particular case here, in our notation. So let's just put that down as well. So over here, this could be layer 1. And that's going to be layer 2. Make sure that's vertically aligned. And then finally, that's going to be layer 3. There we go. It's kind of like our alignments are ready. So these are, and I could really call these layers, but hopefully that we can see that. Maybe I can draw a dotted line as well somewhere in between. I don't want to like over mess it. That's the only issue. Line, can we draw some sort of dotted line there between the layers? So something like that. Very fine dots and very light colour as well. So something like, there we go. Nearly invisible. So too invisible. It'll have to be green or something like that. There we go. So we just kind of like segregated our layers out as well. So copy that and paste it here. It's kind of like, that's just a separation of the layers so that we can see like the different pieces that we're talking about. And I'll hit save and close now. And hopefully, wherever that's gone, because I've just lost it. Oh, there we go. Ended up being relatively large, but that's our layers. That's our neural network. That's what it's talking about. So it's kind of like the mathematics, and it's sort of like how it's linked in. I wonder if I could. There we go. I squeezed it onto one page there. So we sort of like got some mathematics for backpropagation, and now I'm going to read through the actual documentation itself. So yeah, what I'm going to do is just quickly, or maybe I'll just read through this to start with, and then we'll go back. But it says here in the last chapter, well, at least I'll open it up so I can sort of like refer to it, because I might jump across. In the last chapter, we saw how neural networks can learn their weights and biases using the gradient descent algorithm. Okay, so that's kind of like the key part, or not key part, but like if you're going to look something up, and maybe I'll put it in backpropagation. On gradient descent, so it relies on the gradient descent algorithm. That's what backpropagation does, and I can actually zoom in on this as well because it might be too small to see. So there we go. That's kind of like, this is the notation that was written initially, and this is describing what it means. We're going to go through a bit more about what it means so that we're clear on it, but this W here denotes this weighting. So one of these lines, it's got a weighting between this kth neuron and the kth neuron, which lies in the L-1th layer. So the layer to the left-hand side is L-1th layer over here, and how it relates to the jth neuron that lies in the Lth layer, so this layer over here. So it's talking about sort of like this relationship, this blue line effectively, and the J represents, so like, you know, if this was a J over here, and the K represents if this was like a K over here, for example. So it would look like that basically. So we're talking about this line over there, and L is that layer right there. So we're back. We've got the documentation. I can sort of like maybe I'll create this file and save it somewhere so people can see it. But that's what we're referring to, and that's all in much bigger font now, so it's a bit more visible. Control -1, see if I can. No. Zoom back out a little bit. There we go. It still should be big enough. So that's what we're referring to. And we have this algorithm. It's called the gradient descent algorithm. We don't know what it is necessarily yet. That's what we're going to be talking about. So there was, however, a gap in our explanation. We didn't discuss how to compute the gradient of the cost function. Right? What is this cost function? It's kind of like the cost of getting it right and wrong, effectively, is what the cost function is. So there's a cost between each of the layers. It says that's quite a gap in this chapter. I'll explain the fast algorithm for computing such a fast algorithm for computing such gradients, an algorithm known as backpropagation, and I think this is one of the popular algorithms. And I'll like go and have a look at it. I think I did this. I don't know where my search went, but backpropagation, and we can see a whole bunch of stuff over here. If I can zoom in, maybe, or so forth. Let's see. There's going to be tons of these anyway. But what we got is inputs, and then we're sort of like measuring our what's called this cost function, this error thing. So if I go onto too many websites, it's like pop up with all the different stuff asking you to subscribe, unfortunately, which gets a little bit tedious. But anyway, that's what it is. Here's one that's got a little nice diagram of backpropagation as well. So we sort of like we're doing our forward computation, and then we do this backpropagation some way, and there's a compute error and so forth. So we can see the mathematics around it. So that's what we're talking about. Anyway, backpropagation was originally introduced in 1970 or in the 1970s, but its importance wasn't appreciated until a 1986 paper. I won't click on this paper. Ooh, should I? Famous paper. I've never seen this paper myself, so I'm tempted to click on it. I don't know if we'll get to see it. Okay, it's a purchasing thing, so we won't look at that paper at the moment because I'm not buying it. But I guess we just have to take it as it might be, that like the information is there, but yeah, we're not going to be able to look at it as such. But anyway, it's referring to this paper. The paper describes that how several neural networks where backpropagation works far faster than early approaches to learning, making it possible to use neural nets to solve problems which had previously been insoluble. I think that should be insolvable, not insoluble. Today, backpropagation algorithm is a workhorse of learning neural networks. Now, what is backpropagation, right? In really, really simple terms, if we kind of like got this chart, this thing over here, and we sort of like, I guess we like put a ball over here. This ball is going to go where the gradient is, and the gradient is delta y by delta x. So imagine that we had our axis, so like over like this. The slope at any point is what is the gradient, and here we can see the slope is downwards. So we've got this our propagation, this gradient descent is the ball is going to go from wherever the point is, it's going to go down. It's going to descend down the gradient. Now, if we did continue this like that on this side, and we had in the ball like went right down, it might then come back up, roll back up the other side, and Bitcoin's trading. That's what that is, and it would have to go back over there like that. So that's pretty much that component of it. So I'll just interlude with a little interruption, but here's Bitcoin trading, so a little algorithm that's running in the background. So every now and again you'll hear that noise. So this ball, but ultimately what's going to happen is the ball is going to end up in this stable position, and that's basically what gradient descent is. We're going to descend towards the lowest gradient. Now you can imagine, like other people do these great videos and things where like you can imagine this in 3D as well. So like where you're at the crest of or the trough of a valley of a hill effectively. So you sort of like roll to the bottom of a hill, and you're going to stay there. So that's effectively what backpropagation in simplistic terms is talking about. So we'll continue. This chapter is more mathematically involved than the rest of the book. If you're not crazy about mathematics, you may be tempted to skip the chapter, but I actually am quite interested in this. And to treat backpropagation as a black box whose details you're willing to ignore. So you could have sort of like taken the picture that I did set. I wonder if I can do an undo. This picture over here that I did set. He's like, oh, we'll take this picture, over here, and I'll get a drawing app out at some point. So we can take this picture over here, and that's it. That's all we need to know, and we don't need to know any mathematics of it. So you could get away with doing that if you wanted to, but I'm going to choose to not do that. So why take this time to study these details? The reason, of course, is understanding. Okay, there's no other reason to do it. At the heart of backpropagation is an expression for the partial derivative dc by dw of the cost function c with respect to the weight w. So we have some cost function. So we have cost. I'll put this in. There we go. So on a new line, we have a cost function c and weights w. So we've got something like this. This is what it's talking about. And what we're trying, weights or a bias, okay. Sometimes called weights and biases. For a bias B, okay, we're going to use weight, and what we're looking for, we are seeking the rate of change in the cost function relative to a change in the weights. And that is this expression here. So if I do and insert a working kit new equation there, we are doing, and let's just get this quite simply, and if I've even got the delta, but we're looking for the change in the cost function, so delta C over, and then the change is small increment in the weight, so dc by dw, something like that. I wonder if I got a partial b. No, I don't at this point, not at least not in the Greeks over here. I might slightly change that because I do have other things here. Well, okay, this is a delta as well, so delta y over delta x. Yeah, there is other notation here. Okay, I can just insert symbols, I think, and I just wonder if I got a partial b in there. Don't know if no, it won't be in here, so insert special characters, and then I wonder if it's a D like that. We've got a partial D there, which is sort of like a curly D. I don't see one. Oh, there we go. That's the best I'm going to be able to do. But that's good enough, actually. Looks quite right. That's it. So we're looking at dc by dw. So that's effectively what we're looking at over there. So the partial derivative dc by dw of the cost function with respect to any weight in the network. And in particular, the expression tells us how quickly the cost changes when we change the weights and biases. So that's really what we are actually talking about. So I'm going to take that as well. And move back. I might even move this over here. So, and while the expression is somewhat complex, I don't know if it is complex really, like once you understand it, sort of like it's just letters, and actually what we're talking about is just really these 4 letters over here, or at least these 4 letters here, W, which is actually the blue line that we're talking about, L, which is the layer, J, which is the JAF neuron, and K, which is the K, which is the case neuron, JKL. Okay, I'm just going to be very careful about one thing. I just want to make sure in the picture that I'm similar. That's 2,4. That's the 4th one here. It is like that. It's weird to look at, but that's J and K. But the kth one, which is actually the earlier one, it's referring to the case neuron, so the previous layer. So we just got to get a hang of understanding what this notation means. So yeah, we have it all in there. So and that's basically notation. So that's what it is. So we continue on then and go to let's keep on reading down. Where were we? Yeah, so we haven't come to our picture yet. We're about to. And while the expression is somewhat, it also has a beauty. So while the expression is complex, it has a beauty to it, and the beauty is that like it works for each single neuron and every single weight and bias. So that when you combine them all together, the sum of all of them does give you the actual backpropagation, like the continuous backpropagation that we're seeking. So backpropagation is now just a fast algorithm for learning. It gives us detailed insights into how changing the weights and biases changes the overall behavior of the network. That's well worth studying in detail. With that said, if you want to skip this chapter or skim the chapter or jump straight to the next chapter, it's fine. I've written the rest of the book to be accessible even if you treat backpropagation as a black box. You don't have to understand it, but it's helpful to it is helpful to understand it because it gives you a feel for how the weights and biases change and sort of like, you know, how quickly we might be able to compute or where the errors are in computing. Because if our backpropagation is like too heavy, I don't know if I can do an undo on here again, but if it's too heavy, maybe we like descend far too fast and kind of like go through and like sort of like break our mathematics because we haven't done it. And if it's too slow, so if it's like the algo will be slower because you have to do like loads of steps. So, and I've seen things about this. It's kind of like getting this right in the neural network, like what is the right way of doing it, and maybe there's assumptions or things that need to be made, but that's all part of it as well. So there are of course points later in the book where I refer back to results from this chapter, but those points you should still be able to understand the main conclusions if you don't follow all of the reasoning. So we're going to try and get an understanding of the reasoning. So warm up. Right, here we go. A fast matrix-based approach to computing the output of a neural network. Now Python does this really well, you know, and kind of do want to jump into the Python code. but maybe it's a bit too early because we're on our beginning mathematics, if that makes sense. But afterwards we'll have things like scikit-learn and so forth that will do a lot of the stuff, and some of the other modules. I'm just trying to think what some of them are. I'll come back to. I'm sure we'll get around to it. But basically, like there's proper machine learning or neural network models in Python that are like very sophisticated and do a lot. But yeah, let's continue then. Before discussing backpropagation, let's warm up with a fast matrix-based algorithm to compute the output of a neural network. We actually already briefly saw the algorithm near the end of the last chapter, but I described it quickly, so it's worth revisiting in detail. In particular, this is a good way of getting comfortable with notation used in backpropagation in a familiar context. So let's begin with a notation that lets us refer to the weights of a network in an unambiguous way. Now, if we don't get our head around this, then we kind of like will struggle. So this is kind of like, once we've learned this component, to like understand what we're talking about, I believe that we're kind of like pretty much all the way there for the mathematics, and we're ready to like, we've done our notation here, so we really understand what this means. It's the weight, so effectively this weighting here, of layer 3 between the fourth neuron, 1, 2, 3, 4, and the second neuron here, 1, 2. That's what it's referring to. It's referring to this. And so if we have like W2, that will be this referring to this layer, and then I don't know 1, 1, then it's going to be referring to this particular line here because it's the first one and the first one here. So, and if it was 2, 1, it'd be 2 here, or it'd be 1 here and then 2 over there. So we've got to be careful about which way around the I and the J and the K are in our talk. So that's really it. And a diagram below shows the weight of a connection for the fourth neuron. Right, that's the 4 over there. In the second layer, so layer 2, I guess, fourth neuron in the second layer, layer 2. I'm just going to be careful of one thing there. That's layer 2, okay. To the second neuron in the third layer. So to be careful that I don't explain it incorrectly myself. Oh yeah, we're always talking about the L-1 layer, so the layer is at the top. So that's why it's a second layer. I'm trying to get my head around it for the first time too. So this here, but it's referring to the L-1 layer. So this means layer 2. So the fourth neuron in layer 2. So it's talking about this line over here. So we still got to get our head around this. But anyway, the mathematics, like once we've got this in our head, mathematics is going to take care of the rest of it. Because all we're going to need to know, like beyond that, is the WLJK. That's basically it. We need to remember what layer that it's referring to. It's always referring to the layer prior to it. So if L was 1, or if I guess here L would have to be 2 to refer to the first layer. And so forth. So that's basically it. So if we wanted to talk about this connection here, we're talking about the L2 connection. So this is L2, and it's referring to the previous neurons, the neurons in the previous network that where it comes from. Anyway, this notation is cumbersome at first. Well, it is. You can still like see me struggling to get to grips with it myself, but then like once you got to grips with it, it's okay. And it does take some work to master, but with little effort, you find the notation becomes easy and natural. And it kind of like does. So like, I go through it just like one final time here, but this is basically layer 2. It's referring to the previous layer, so we're always talking about the previous layer. So this is 2, and in our notation this is 1, but we can see those already, and we're talking about these connections here between the 2-1 layers. So we're literally talking about how many of these we count down and how many of these ones, like which connections we're referring to between any of these. So that's basically it. One quirk of the notation, and you just saw me got stuck earlier on it, but here we go, is the ordering of the J and K indices. Because you like to think that the J one's here and the K one's here, so it sort of like goes in order, but it didn't. It was the index of the previous one comes second, which is a little bit annoying, but maybe you can think of it, I don't even know, as this is the here, this is the one that we've got in focus. So that's layer, so that's why we use this. That you could consider that 3 to be talking about layer 3, but we're going to go from 2 to 3. And this one here, so these two pieces give us this. So the reds give us this, and then this one here gives us this. That's kind of like the way to think about it. Now, we could have said that this is the 3 and 2 thing. I imagine that why that's dropped, because it's actually like there's 4 data points. Kind of like, if we want to get the reds, we need 2 coordinates. We need its layer and its count. So this is 1, and this is, I'll do that in red. This is 1, and this is 2. And then if we want our blue layer, well, we know that we're talking about layer 3. So the blues now is layer 2. So I could sort of like do it here. This is the actual second layer. This is layer number 2. And this is index number 1, 2, and they're in blue now, 3 and 4. So we sort of like, we've now got a much better understanding, because I've color coded it in a way, of what the WLJK actually means, and how it translates. And finally, it means this actual line over here going in this direction. And if I guess if we swapped the notation around, then it'd be the line going the other way, because that's how mathematics works. It's symmetrical and works like that. Another Bitcoin trade takes place. There we go. So that's kind of like really it. But yeah, one quirk is the ordering of the J and K indices. I might just take this little piece here and go to, not over there, but where was it, the maths thing here. And I did have a little bit of room, so I can paste it in there, paste without formatting, one quirk. Just so that we sort of like know what we're referring to, and so forth. But here 2 referred to, we could see this 2 here, and I could color code it. Maybe I should, but I won't. But this 2 here referred to this 2 over here, and this 1 here. Oh, I've got to be careful, because I should have done that. I probably should have done it the other way. It might, I've backwardized the notation here, because I should have used 5-1, I guess. So I will actually amend that, because I can't have that being wrong. So let's just go and amend it. It's actually going to be, I've got to be careful of this as well, but this is referring to 5 and 1. That's the way round that it's going in terms of what we're doing. So there we go, learning our notation. So there we go. So 5 is referring to 1, 2, 3, 4, 5. And really, actually, I should have coloured that 5 in red. There we go. And this 1, now I'll put it in green here, is referring to the K1 over here. And if we did, but we don't need to because we know that this is the ELF minus 1, so there would be a 1 here. If this is a 2, that's got to be a 1. And that's basically it. So that's all of it. And so now we've like fully described. And that basically tells us where any one of these like neurons, where any one of these weightings are. So, and here we go. You might think it makes more sense to you to use J to refer to the input neuron and K to refer to the output neuron and vice versa. As it is actually done, I'll explain the reason for the quirk below. So it's probably going to explain it in very much a similar way. We use a similar notation for the network's biases and activations. Explicitly, we use B of L and J for the bias of the Jace neuron. So we've got the weights and the biases. So B is this one here, for example. It's of the J neuron. So B is going to be an actual value. So we've got neuron 3. So 1, 2, and 3. So that's a J neuron, and L is the layer. So we're literally counting across the layers. So that's our layer here, and we're counting down over here for our component. And those are the two indices in the biases. So this 3 here is how far down we are. So I could literally write it like B, and then it is down. And the top component, the superscript, is how far across. And that's kind of like pretty much it. So it's no different really if we're sort of like, you know, in anything that we're doing. If we're talking about a graph, for example, like on our Cartesian coordinates, and we said, you know, we sort of like want to get this point over here, right? In order to do that, we have to sort of like come to some agreement as what that point is. And we can say like, you know, it's got an X component and a Y component. And in order to talk about it, we'll have to call it X comma Y. Now, if somebody wrote Y comma X, again, it's just a convention. We have to understand the convention. The convention actually becomes, what this guy's saying is the convention actually becomes quite logical for various reasons. We'll go and see that in a bit. But we never had to have this system here. We could have had like polar coordinates, for example. So we could have some sort of north pole like that. And then we could have had, you know, the same dot over here. But now we got our origin over here. And what we want to do is compute so like this line here. And now we're going to have, this line is going to be of radius r, and its angle is going to be of angle theta, which is the angle that we sort of like moved around from our origin. So this is so the top one's Cartesian coordinates, the bottom one's polar coordinates. But now in order to describe this point, we now need to give it, like, for me to talk to you, or for us, we now need to have an r. I need to tell you the radius of how far it is from here, and then I need to tell you of a theta like that over there, and then we're in line and we can sort of like talk to each other. So this B, this bias, in order to say what bias we're talking about, we just need our coordinate system, and the coordinate system for a neural network looks like, for the biases of a neural network at least, looks like that, and the coordinate system for the weightings had the W, L, J and K. So that's all it was, is how to get between the components and what we're talking about for all of them. So, and I should actually put the biases in the other document as well. So down here we use similar for the biases, right? B, right? And in fact, I'll put the biases there, and then I'm going to do new equation, because it's going to be this thing again, which is B, and then what was it over there? J and L, I believe it was over there. Let's stick with the same notation. Yeah, B, J, and L. And in a way, it's easy. It would probably been easier to start with the biases for the description, but you know, we didn't. We started with the neurons. But probably if I steal some of this, the whole lot of it, over there, and I'll go back in, and this time not talk about the weight, so I'll double click on it. I will remove this whole weight thing. And actually I control Z it, Z. I'm just going to change it to a B, and it's a bit cleaner to do. Still not amazingly clean, but we can see the two indices here. We're in layer 2 here, so we've got the 2 over there, and we've got the neuron, the bias over here, and this one literally now is that bias over here, this exact one there. You can get it right in there. There, perfect. Look at that. And let me just. I can't do. I can format that and then ping. There we go. So. Wonder if I can shrink these lines a little bit. They don't need to be as long. There we go. Shrink that. So these J's here refer to the actual neurons, themselves, but each neuron actually has a value, its bias value. So this neuron here is 1, 2, 3, 4. Like, let me be able to count properly. That should have been 5,2 over here. There we go. Get the right biases. And we saw that the weighting was similar. So I'll hit a save and close over there. And that's what the biases look like, and it's a little bit clearer with the biases because now we've only got 2 indices rather than 3, and we know what that particular bias is and how to get across and, like, you know, count it as it was. So maybe I could put sort of like an axis on this, which is could do. I mean, if I was to put an axis on, wouldn't be the world's best axis, but it's a bit like actually when we do coding for the screen starts in the top corner, so that's the 0, 0 position. When we're doing graphs, like when you're at school and you're 10 years old, you start from here, from the 0, 0, so the bottom left. When we do screens and stuff, so like computer monitors and stuff, we start from the top left. And here we're kind of like, in a way, starting from the top left, because this is our layering over here. If I can move that down a bit or something. That's our layering over here. And this one here is our counting system down here. So that's our counting method down here. Now, in our first layer, in our L-1th layer, should I say, we've only got 4 neurons. We can only count down 4. In our L layer, we've got 8 neurons. We can count down 8. And in our L+1 layer, we've got this. So we could say that we could call this layer 1. Well, we have done. We've called this layer 1, layer 2, and layer 3. And we count down. So now we've got a way of identifying any single component. So if I said, I don't know, 3, 3, 2, that's this one here. This is 3, 2. And if I said 1, 1, it's this one over here. So we know all of our bits, and maybe even sort of like delete. We don't need to do that. I could sort of, like, if I wanted to, copy that and paste it and stick that over here, because this is B, just for clarity, 3 and 2. So that's what that one looks like, and maybe I'll turn it to a different colour just so we can identify that they're not the same thing. Or I'll keep the biases the same colour actually. Don't need that there, and hit save. I'll make these axes a bit thicker so that it's more line thickness. There we go, 4, and thickness over there, 4. There we go. So we can sort of like see that's our coordinate system. In fact, I can even join them up nearly. Look at that would be. I will join it. There we go. It's like joining it there. So we've now got a coordinate. This is literally our coordinate system. So hit save and close. And it's moved on to the next page. So I'll shrink it a tiny bit. Maybe I will shrink it a tiny bit more. I know I have to keep it there because otherwise I just wonder how much I can shrink it before. There we go. Fits on one page now. So yeah, that's our biases now, and the biases are easier to understand. So we use a simple notation for the biases, okay, and yeah, it's easy to. The following diagram shows the examples of these notations in use. So we see that, and with these notations, the activation ALJ, so here's another acronym, I could have, I guess, put that in there, of the J's neuron in the ELF layer is related to the activations in the ELF minus 1th layer by the equation, and that's the beauty of this, by the equation, compare equation 4 and surrounding discussion in the last chapter. So we will, I think we're going to have to jump back to the last chapter, but basically this activation here is related to all of these preceding weights and biases. So we're going to have a bias, and that's basically it. And it's going to be the sum of all of these. So because we got the sum of all of the K weights that come in on the, so it's going to be from the previous layer. So this layer here is going to be determined by this layer, by the previous layer, and it's going to be determined by the sum of all of these pieces here, and well, the sum product of all of these pieces here with their activations, plus the bias as well of it. So each one of these will have a bias, and I think that's pretty much it. So I kind of like might stop at this point, only because I think, I don't know, I was just trying to look to see how long that this video has gone on for. We've crossed the hour mark, so I'm not going to go any further on this, but we're kind of like, I'm not going to say we're at the end of it, but we weren't very far from being at the end of everything. But what we have done, and we've understood, or we've set up a framework now of our notations. We've set up a notational framework of what a weighting looks like and how we can refer to it, and what our bias looks like and how we can refer to it. And I guess in the next piece we'll probably look at the formulas between them for the actual purpose of finally getting towards computing the back propagation. So I think I'll leave it there, and yeah, we'll come back to this. What I will actually do is I will take this over here, and I will. We've got a chapter 1, and I didn't actually look at it. I have been through this before, I think, quite a while ago. Like we're talking like months and months ago, so it's not immediate in my memory. But we can see there's lots of stuff here that we can kind of like learn and take out of this. But I'm going to put this little link kind of like, I think I should put it over here. I'll hit return so that we actually get the actual link of it, and hopefully, yep, there we go. That will fit it in quite nicely. And the only other thing is why is all of this? So everything there should be normal text, and that one should be normal text, and that should be normal text, and that should be normal text. Okay, all my writing was extra big. That makes a little bit of extra room. The writing was followed on because I made the actual formulas their size 18 there. This formula as well is size 18, but we want the formulas to be a bit larger. I might actually make this one a bit larger just so that we can see. There we go, so it's nice and clear. And yeah, that's pretty much it. So we're going to get on to the formulas next. So and the formulas are going to be dot, there we go. The formulas connect, or we could put or show relationships between the nodes of the neural network. There we go. And that's it. I'm going to sign off. If you found this useful, hit the thumbs up button, the like button, and the follow button. And if you didn't find it useful, still hit the thumbs up button, like button, and the follow button. If you've got any comments, definitely put your comments in there. If you've got improvements, put your improvements in there. If I've made like blundering errors, definitely put those in there as well to like highlight where they are, because it's quite useful, because I've gone through this literally without having even looked at the text or even pre-read through it. So this is actually a first look. So if you find if you think that anywhere that I have missed something or made a really like blatant error, just put it in. Definitely put your comments in too, if like things that you feel will add on to this. And yeah, we'll go from there. I'll do another session at some point, but basically where we're at is the backpropagation for neural networks. So that's pretty much it, and I'm sorry.